In this video, I am going to discuss chapter 4 from your textbook, randomized blocks, Latin squares, and related designs. Actually, this video we will focus on randomized blocks, and I will make another video for Latin squares. So let's talk about the randomized complete block design, or in general, the blocking principle. Last chapter, chapter 3, we studied analysis of variance for a single factor. Now, the RCBD design is an extension of ANOVA. So, what is this blocking principle? Uh, Blocking and nuisance factors. So, uh, we are going to talk about experiments where we will come across nuisance factors, and we need to devise techniques to block those nuisance factors so that they do not affect our experiment. So one of the technique to block those nuisance factors is the randomized complete block design, or the RCBD. It is an extension, as I was saying before, it is an extension of ANOVA to the RCBD. There are other blocking scenarios that we are going to discuss in another video, particularly the Latin square designs. So, blocking is basically a technique to deal with nuisance factors. And what is a nuisance factor? What can you classify as nuisance factors? As we have learned before, in any experiments, the experimenter is interested in the impact of certain factors on the output. So the experiment is all about those factors that experimenter is interested in, and their impact on the output. But at the same time, there are several other factors, variables that are affecting the experiment. Some we can control, some we cannot control. Some can be, and so far we have grouped them as standard error or standard noise. But there are some factors that they have, even though the experimenter is not interested in them, they have a significant impact on the output as compared to the standard error. So we have to consider them differently. We have to give them special consideration. So, a nuisance factor is a factor that probably has some effect on the response, but it is of no interest to the experimenter, right? However, the variability it transmits to the response needs to be minimized. So, some examples of nuisance factor is batches of raw material. Suppose you are working on an experiment in chemical industry, and different batches of raw material, they can cause variability in the process, chemical process. Even though we are not interested in studying the different batches, but we need to be aware of that. We need to be aware of the variability effect that different batches of raw material bring into the process. Operators can be another nuisance factor. Different operators may have different skill set, may have different training. So uh, two different people performing the same job can do it differently and can have different results. Pieces of test equipment, time, it can be another nuisance factor. When the experiment was conducted, maybe day shift, maybe night shift, days versus night. So these are some examples of possible nuisance factors that you will come across. Many industrial experiments, they need to involve blocking in order to control these variables that we just discussed, right? If if they fail to block, then that can affect their experimental results, right? That is a common flaw. Failure to block is a common flaw, and that can have bad consequences. So, continuing that discussion on nuisance factors, there are different types of nuisance factors or nuisance variable. So, let's go over them. The first group of nuisance variable is known and controllable. That means we the experimenter or we know those nuisance variable in advance, and we can control them. For example, here, if we talk about an operators, right? So we know that different operators will do the experiment differently, or their individual differences will affect the result of the experiment. But we can control this way. We know this variable, and we can control this because we can pick and hand pick uh, some operators, and we can keep them consistent. So those are easy ones, right? The variables are known and controllable. So in that case, we can use blocking principle. If the nuisance factor is known, we know them, but we cannot control them, uncontrollable. So if you think of some examples, atmospheric conditions, right? If the experiment is performed uh, outside, the atmospheric conditions such as temperature, humidity, and factors like that, we know them that those are factors, but uh, we cannot control them, right? And there can be many other examples, the factors that we know, but unfortunately we can't control them. Then how can we deal with them if we cannot control them? So sometimes we can use the analysis of covariance technique to remove the effect of such nuisance factors from our analysis. Then the last group is the nuisance factors that are unknown and uncontrollable. So that's those are difficult ones, right? Because we don't know them in advance. So obviously we don't know them, so we cannot control them. So those are sometimes called as lurking variables. And the best thing we can do about them is, we hope that randomization, we talked about how randomization is important in design of experiments. So you have to pick and choose your experiments randomly, right? So we hope that randomizing your experiments can balance out the impact of those nuisance factors, lurking variables across the experiment. And the last bullet point, sometimes several sources of variability are combined in a block. So we are combining several different nuisance variables into one block. And that block can become now an aggregate variable. So it is easy to deal with that block. So I guess we can look at an example to understand these ideas better. So many of you have taken the material science course, and you have performed the hardness testing lab in that particular class. So let me show you a picture of the lab setup. So this is a typical hardness testing machine, where uh, you have this sample material that you want to uh, check the hardness of that material, right? And then you have this diamond indent. They're mostly made up of diamond, this indent. So this machine, you apply a pressure, downward pressure, and you press that point against the test coupon or this material. And based on the indentation, that how much indentation that point makes, it gets we have a dial here, hardness dial, that converts that number into the hardness testing result called RHC. So Rockwell hardness number, right? RHC number. So that's how you do a hardness testing lab. Now the problem here is, we wish to determine whether four different tips produce different mean hardness reading on a Rockwell hardness tester. So if we use four different tips from maybe four different suppliers, uh, in ideally we would like to have exactly the same hardness uh, testing result, right? We need to have the same mean hardness reading for our tester, because the material hardness is not going to change. It's the same material. But since these tips from four different suppliers, ideally they should produce the same result, but we want to check that. We wish to determine whether four different tips produce different results or the same result. This type of studies are very common. They are called gauge and measurement systems capability studies, and that's a good area for application of design of experiments. So far, so good. So, in terms of the analysis of variance, we know that our the problem statement. Let's go step by step. The problem statement, it can be summarized as: determine whether four different tips produce different hardness reading on the Rockwell hardness tester. Right, that's our problem statement. Then, what is the response variable? What is the output variable? It's basically hardness reading that we are going to measure. And what is the factor, or in another word for that is, what is the treatment? The factor or the treatment is this tip, four different tips, right? The experimenter is interested in studying the impact of the tip on the hardness testing result. So far so good, right? uh, but that would be just a single factor analysis of variance problem. But this chapter is about randomized complete block design. So is there any nuisance factor we are looking for? So let's talk about that. Assignment of the tip to an experimental unit, that is a test coupon. So basically this test coupon here, right, is what we are talking about. The test coupons, we are going to use different test coupons in the experiment, and different test coupons can bring they are not the same. Ideally they should be same, but there can be differences between various test coupons, right? They may be coming from the different brands or different batches of raw material. So there can be differences from test coupon to test coupon, and that can add variability to our experiment, and that's what we want to control. So that's what make it the completely randomized experiment, the randomized block design. The test coupons are source of nuisance variability, as we said. Now, what type of nuisance factor is this? If you go back to this slide, how would you classify it? Well, we know it, right? It is a known variable. The test coupon is going to cause variability. We know in advance, it's known, and to some extent it is controllable. The choice of the test coupon can be to some extent controlled by the experimenter. Alternatively, the experimenter may want to test the tips across coupons of various hardness levels, right? We can choose for the experiment, we can choose the coupons of various hardness levels. So there is a definitely a need for blocking this nuisance factor. There is a need for blocking the effect of test coupon variability on the hardness testing result. So we need to conduct this experiment as a RCBD, randomized complete block design. How can we do that? We can assign all four tips to each coupon. So we can so each test coupon can be tested with all four points, because one test coupon itself is a very homogeneous unit, right? Each coupon is called a block. That is, it's a more homogeneous experimental unit on which to test the tips. So we are going to test all four tips on each coupon or on each block. Variability between blocks can be large from coupon to coupon. Variability within a block, within one coupon, should be relatively small. In general, A block is a specific level of nuisance factor. So one test coupon is a specific level of nuisance factor. Then another test coupon will be another block, and so on and so forth. A block represents a restriction on randomization, and all runs within a block are randomized. So when you are using four tips on this block or one testing coupon, uh, we got to make sure that we are randomly assigning the order in which we are going to test each tip on the coupon. Should that order should be random. We don't want to everything that we do in design of experiments, the experimentation, we always try to randomize the sequence of experiments. So all runs within a block are randomized. So here is how it looks like. Suppose that we use b is equal to 4 blocks. So letter small b is used to define the number of blocks or the level of blocks. So we are going to use 4 blocks, 4 test coupons. So here is a test coupon 1, 2, 3, 4, and we are going to test each tip on each of the test coupon, but we are going to randomize the sequence. So you can see here tip 3 will be tested first, tip 1 second, tip 4 third, tip 2 fourth, and so on and so forth, right? All randomized fashion. So it's a two-way structure. We have two dimensions. One is the test coupon 1, 2, 3, 4, and we have tips 1, 2, 3, 4. And our factor, we are interested in the effect of tip, not the effect of test coupon, but we want to block the effect of test coupon. So if you write the null hypothesis, the hypothesis for this problem, I will come to that in a minute. But let's uh, discuss how can we extend the ANOVA concepts that you studied in last chapter to the RCBD. Suppose that there are A treatments or A level of factors. In our case, the factor is tip and A is equal to 4 because there are 4 tips. But we are generalizing this mathematical framework now, right? And B blocks. The blocks in our case, test coupons, and there are 4 test coupons we are using. So B is equal to 4. We have A is equal to 4 and B is equal to 4. So let's write down a basic statistical model. We can also call it effects model for the RCBD problem. Any individual observation Yij means our experimental result, our hardness testing result. Like this table, after performing these experiments, we're going to write down hardness testing results that we achieve, right? So any individual values Yij, if there was no variability, if for example, let's assume a perfect world where there is there is no variability between the 4 different tips, and there is no variability between the 4 different test coupons, and also there is no standard error like all other factors that we classify as standard error, such as atmospheric conditions and whatnot. So let's say there is absolutely no variability and utopian situation. Then every time we perform the experiment, we should get the same hardness, mu. It's a population mean, right? Mu. Every time we perform the experiment with whatever tip we use, with whatever test coupon we use, we're gonna get the exactly same result, same hardness testing result, mu. There is no variability whatsoever. But that's not gonna happen, right? In reality, every time you conduct the experiment, you're gonna get the different result. Now, that variability, every time you are performing different, you are performing the experiment, you are getting different result. That variability can be classified into these 3 groups. So we have the mean, right? Plus the individual observation consists of mean mu plus tau sub I. Tau sub I is basically the variability contributed by the factor, the tip in our case, plus beta sub j. is the variability contributed by the nuisance factor by the block. In our case, it is test coupon plus epsilon ij, where that is the standard error. So all these three sources of variability will basically give us each time different hardness testing result. So tau sub I varies from 1 to a levels of factor, four factors, four tips. J is equal to 1 to b, beta j. The b means the level, b levels of block, or four levels in our case, four levels of test coupon. And the hypothesis is mu1 is equal to mu2 is equal to dash 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 is equal to mu sub a. In our case, mu1 is equal to mu2 is equal to mu3 is equal to mu4. That means the the mean hardness testing result for tip 1 is equal to for tip 2 is equal to for tip 3 is equal to tip 4. So equality of means is our null hypothesis, and alternative hypothesis will be at least one of them is different. At least one of they all can be different from each other, but at least one of the tip is producing different mean hardness testing result. So those are our hypotheses. And then we take the ANOVA partitioning of total variability, just like we did in the last chapter. Uh, so the variability, its total variability is given by this individual observation minus y bar dot dot, which is the grand average of all the readings, all the observations, whole square. And then we sum it for all yij's, right? All the observations in this table, all yij's. So we take that total variability and then we partition that into these three factors: tau sub I, beta sub j, epsilon sub ij. So you look at all these mathematical analysis here that will eventually lead to what we are interested in is this bottom row here. Sum square total, this one, is equal to the variation, total variation is equal to sum square treatments or sum square factor, this variation contributed by the factor that the experimenter is interested in studying, plus sum square block, the variation caused by the nuisance factor block, plus sum square error, standard error. We also need to know, as we know, we cannot compare the sum square to each with each other directly. We need to compare the mean squares. And how do we get to mean squares? We divide sum squares by respective degrees of freedom to get the mean squares. So let's talk about degrees of freedom. So sum square total uh, is AB minus 1. A times A is factor level, B is block level. So basically total number of experiments. If in this table we have four blocks and four coupons, so we have 16 unique experiments. 16 unique experiments. So our degrees of freedom would be 16 minus 1, 15. So total degrees of freedom would be 16 minus 1, 15. Sum square treatment or the factor degrees of freedom, we have four factor levels, a factor levels. So degrees of freedom can be given by a minus 1. Factor degrees of freedom is given by a minus 1, or in our case 4 minus 1, 3. Then blocks degrees of freedom is given by b minus 1. B levels of block, once again we have four levels of block, so b minus 1 is the degrees of freedom for the block. And for error degrees of freedom, you can subtract from the total degrees of freedom, you can subtract the degrees of freedom for the factor plus degrees of freedom for the block. Whatever is remaining is the degrees of freedom for error. Or alternatively, we can do a minus 1 times b minus 1. Okay. So we can calculate sum squares, we can calculate degrees of freedom, and then the ratios of some square to their degrees of freedom result in mean squares. And then ratio of the mean square for factor, when we calculate mean square for factor, we want to compare it with error. That means we want to compare variability caused by factor is how significant it is as compared to variability caused by error. So if it is highly significant, that means the null hypothesis will be rejected. That says uh, all the means are equal. No, because the variability caused by the factor is highly significant. That means all those means, mu1 is equal to mu2, cannot be true. So we want one way to compare is to divide mean square factor by mean square error. So that's what is the this statement says here. Therefore, the ratio of sum of squares to their degrees of freedom result in the mean squares, and the ratio of the mean square for treatments to the mean square error is basically our F statistic, F distribution, right? That we can use to test the hypothesis of equal treatment means. So here is the classic ANOVA table. We have source of variation. What are different sources that are causing variation in the observations? We have sum of squares column. We have degrees of freedom column. Then sum of squares divided by degrees of freedom will give us mean squares. And mean square factor divided by mean square error, it will give us the F value. Okay. So and there are three rows. One row is for factor. One source of variation is the factor or treatment. Another source of variation is we didn't have this before because in last chapter we were not talking about nuisance factors. We had only three rows: factor row, error row, and total row. In this chapter, now that we have introduced the idea of nuisance factors, we need to have a row for them, right? Because that's another source of variation. Then the third source of variation is standard error, and we have the total variation at the bottom. So we for every problem, this is the basic table that we need to complete, and then based on the F value, we can decide whether to accept or reject the null hypothesis. So manual computing is going to be very difficult. There is lots of math is involved. That's why we can use software. There are different type of software like statistical software that are available in the market that you can use. One of them is called Design Expert. There's another software called Jump. We have Minitab, then IBM SPSS, or we can simply use Excel. In our case, we are going to use Excel to perform these calculations. So here, if you want to do it manually, here are the formulas for sum square total, for sum square treatments, for sum square blocks, and then sum square error is basically subtract sum square treatment and sum square block from sum square total. You're gonna get sum square error. Uh, but we are going to skip manual computing. We're going to use Excel. So let's so far I this first problem that we discussed was just to uh, create a framework of understanding for you. Right now we understand how the RCBD problems are solved, and the ANOVA table that we need to complete for these problems. So now I am going to discuss an actual example where we will do all the calculations and uh, show whatever we learned in this uh, video here. The main the basic understanding, the basic framework we will apply to this new problem. So I will stop this video here, and this problem I am going to discuss in the next video. Thank you.